ನನ್ನ ಎಲ್ಲ ವಿದ್ಯಾರ್ಥಿ ಮಿತ್ರರಿಗೆ ನಮಸ್ಕಾರಗಳು ಹಾಗೂ ಆತ್ಮೀಯವಾದ ಸ್ವಾಗತ. So in the last two sessions we discussed differentiability of a function definitions and problems based on the differentiability. Okay. Now in the third session, I am going to discuss a necessary condition for the existence of finite derivative and Rolle's theorem. So these two are one is necessary condition for the differentiability, second one Rolle's theorem. So these two concepts I will discuss here. Okay. Now the statement of the theorem. So this one can also be named as necessary condition for the existence of differentiability. Necessary condition for the existence of derivatives. You can say existence of derivatives. Okay, continuity is a necessary condition for the derivative. Function is said to be derivative, it must be continuous. Okay, theorem statement. A continuity is a necessary but not a sufficient condition for the existence of a finite derivative. This is the statement of theorem. Or every differentiable function is continuous but converse need not be true. Every differentiable function continuous converse need not be true. That means if function is differentiable, then it must be a continuous. If function is continuous, it need not be differentiable. Converse. Okay. If function is continuous, need not be differentiable. Okay. Now we need to prove this theorem. Let f of x is a differentiable at x equals to a. Let us, we are considering function is differentiable. We need to show that function is continuous. Okay. Now f dash of a is equals to definition. F dash of a is equals to limit f of x minus f of a divided by x minus a exists. So this is the definition of differentiability of a function at x equals to a. Correct? Na? Now let us consider f of x minus f of a is equals to, just rearrange, modify this term f of x minus f of a as multiply x minus a and divide x minus a. Again you will get the same. Okay, multiply and divide by the term x minus a. And next apply the limits on both sides. So limit f of x minus f of a as x tends to a. Here limit again x tends to a, f of x minus f of a divided by x minus a into again limit x minus a as x tends to a. So limit f of x minus f of a divided by x minus a is nothing but f dash of a. So here in place of x substitute, what you will get? A minus a, that is 0. 0 into derivative is 0. So limit f of x is equal to f of a. Clear? Na? So what exactly this means? This is nothing but definition of continuity. Is it right? So here initially we are considering function is differentiable. So at the end we are proving that function is continuous at x equals to a. So every differentiable function is continuous. So this proves that every differentiable function is continuous. So again we need to prove converse need not be true. So here I will prove by taking one example. Okay, that is modulus function. Modulus function is continuous but not differentiable. Modulus function is continuous but not differentiable. So rewrite this modulus function like this: for all x greater than 0 plus x, for all x less than 0 minus x, at exactly 0 it is a 0. Now calculate left hand derivative. This is left hand derivative and this one is right hand derivative. By applying the left hand derivative definition, we will get minus 1. Okay, and here for the right hand derivative we will get plus 1. That means LHD is not equals to RHD. Their function is not differentiable. Okay, so hence it is a continuous function but not differentiable. So we can conclude that every differentiable function is continuous, but continuous functions need not be differentiable. See graphically, observe. So this is the modulus function, correct na? Graph of the modulus function. Wait. Okay. This is the nature of graph of modulus function. It's not differentiable means at x equal to 0 we can draw infinite number of tangents. So it is not differentiable. This is by geometrically. Okay. Next. The Rolle's theorem. So this theorem is very important. First statement of the Rolle's theorem. If a function f of x defined on closed interval a comma b satisfies following three conditions. First one, f of x must be continuous in closed interval a comma b. Second, function is differentiable in open interval a comma b. Here we are taking open interval. Okay, in the continuity we are taking closed interval. And third condition, the value of the function must be equal at the end points of the interval. Then there exists at least one point C in open interval a comma b such that f dash of C is equals to 0. This is the statement of Rolle's theorem. So Rolle's theorem states that function is defined on closed interval a comma b which satisfies three conditions. One is function is continuous in closed interval a comma b, function is differentiable in open interval a comma b, and value of the function at the end points of the interval must be equal. Then there is a point in the interval open interval C such that whose derivative of the function at that point is 0. This is the statement of Rolle's theorem. Okay. Now let us see the proof of the theorem. Proof. Since given function is continuous in closed interval, therefore it is bounded. Correct na? There is a theorem. Every continuous function if a function is continuous in closed interval a comma b, then it must be bounded and attains its bounds in the interval. This is one theorem for the continuity. If function is continuous in the closed interval, then it is bounded as well as it attains its bounds in the interval. If it attains its bounds, let us consider capital M and small m be its bounds. Okay, then there exists a point C and D. There are 2 points C and D in the closed interval a comma b such that f of C is equal to m, f of D is equal to m. That means value of the function at a point C is a capital M, that is it's supremum. Okay, f of d is an infimum. After substituting the point c in the function, we are getting capital M. Let us assume that this capital M as a supremum and small m as a infimum. Okay, now either m equal to m, supremum is equals to infimum, or supremum not equals to infimum, possibilities. Okay, so first case number 1, if m is equal to m, then what happens? If supremum is equal to infimum, okay, then what will happen? Then f of x is equal to capital M equals to m. If supremum is equals to infimum means, for any values in this interval, closed interval a comma b, we are getting the same infimum as well as supremum. We are getting same values. So which means that function is a constant. If function is constant, then whose derivative is 0. That is f dash of x is equal to 0 for every x in closed interval a comma b. So in particularly, derivative is 0 when c in open interval a comma b. Okay, hence theorem is true for any c belongs to a comma b. This is for the case 1, when supremum is equals to infimum. Okay, if suppose m is not equals to m, if supremum is not equals to infimum, since f of a is not equals to f of b, at least one point of m, and m must be different from f of a and f of b. Suppose that capital M is equals to f of c, which is different from f of a and f of b. Now m is equals to f of c, that means which is not equal to f of a. So which implies points c and a are different. Similarly, capital M equal to f of c, which is not equals to f of b, that means c and b are different. So from this one we can conclude that c is not equals to a, c is not equals to b. So which implies c belongs to the open interval a comma b, thus c lies between a comma b, a and b. Okay, since function is differentiable in the open interval, and therefore it is differentiable at x equals to c, because c lies between a and b. Okay, now we shall show that derivative is equal to 0. Okay, now two conditions. Derivative equal to 0 means there are two conditions: derivative greater than 0, derivative less than 0. Okay, let f dash of c greater than 0, then there is a delta, there exists delta which is greater than 0, such that x belongs to the open interval c comma c plus delta, then f of x greater than f of c, which is equal to m, which is nothing but supremum, that is least upper bound. So but m being a supremum, but we have x belongs to closed interval a comma b, by the definition f of x less than or equals to m. But this contradicts, so that we can't prove f dash of c greater than 0. Clear? Huh? We need to prove f dash of equal to 0. Okay, that means f dash of c greater than 0, it's not possible. Okay, similarly we need to prove f dash of c less than 0 is not possible. Again here, at f dash of c less than 0, again by choosing a small positive number delta, such that in this interval, so this is GLB, means greatest lower bound, that is infimum. So this is again not possible. So thus we cannot have f dash of c less than 0. So from this we can conclude that f dash of c equal to 0. So hence this is the proof of the theorem. Okay. Thank you.